Alright, today we're going to do Fall 2022 Exam 2 for MA266. So the first problem says, determine the appropriate form for a particular solution to the third order differential equation, and then it gives us the equation, and it gives us a little hint that we'll use later. So the first thing we're going to do is we're going to try and get we're going to use the characteristic equation, and we're going to set that equal to 0. So we are just going to ignore the right side for now. We're going to ignore the homogeneous part. Excuse me, the non-homogeneous part. Alright, so as you can see, they've given us a little hint over here. And so we're going to use that hint, and we're going to use that hint, and we're going to factor our equation. And from here, we see that our characteristic roots are, so from here we see that it's plus or minus 1. And then from this part we see that it's another minus 1. So to summarize, our roots are -1 with a multiplicity of 2 and 1. And so now we can look at our other side. Now we can look at our non-homogeneous part, this cosine x plus x e to the negative x. And we're basically going to guess the form of them. So I'm going to use the different colors for the right side. So I'm going to call it ypg for guess. And so the first guess we're going to do, since there's two terms, we're going to have two guesses. The first guess is for cosine x, and whenever you see a sine or a cosine, you're going to guess a sine x plus b cosine x. And as you can see, none of these correspond with any roots over here, so we're all good. We need to remember that we have a repeated root here, -1 multiplicity 2. And then for the second term, x e to the negative x, we are going to guess cx plus d times e to the negative x. And the reason we guess cx plus d is because the forcing term, what's called the forcing term right here, the leading term right here, x, is of degree 1. So what we need to multiply it in the guess needs to be a degree 1 polynomial. For example, if you had, if it was x squared e to the negative x, then your guess would be something like cx squared plus dx plus e to the negative x. Or if you had, if your term here was just e to the negative x, then technically you have a 1 over here, x to the 0, because anything to the 0 is 1. And so your degree of polynomial 0 would literally just be, well, I guess you could call it cx to the 0, which is just c, and then you have ce to the negative x. So for this one, we have xe to the negative x, which means we need a degree of polynomial 1, or excuse me, polynomial of degree 1. And so this is our guess. I hope that makes sense. And then now we have to cross-reference with our characteristic roots over here to see, to check if we have any duplicates. So it looks like, so e to the negative x, that means our -1 is a solution here. And we can see that this does match, this does duplicate in our characteristic roots. And it's at multiplicity 2. So if we have a duplication and we have repeated roots, so if we have a duplication, we're going to multiply this term by x if the multiplicity is 1. So like if this was e to the x, since the solution here, the corresponding solution here is 1, and there's only one characteristic root of 1 here, then you would just multiply this term by x, so you don't have any more duplicates. But since our solution, our corresponding characteristic root here is -1 with a multiplicity of 2, we're going to multiply by x to the multiplicity. So since the multiplicity is 2, it would be x squared. If we had multiplicity 3, it would be x cubed, and so on. So this is our complete guess with all of our duplications taken into account. This should be the answer somewhere. I think it's... yeah. It's a cosine x and b sine x, but it really doesn't matter. It means the same thing. Okay, so for number 2, it says a damped forced oscillation x of t satisfies the diffie and it gives us a diffie. And then it says the steady periodic solution x sub sp of t can be written in the form, and then it gives us a form, so we have to remember this part. It gives us a form, we have to put the equation in at the end. And then it's asking us what the values of c, omega, and alpha are. So the first thing I'll say is that xsp, the steady periodic solution, is essentially the same as what is like x particular, our particular solution. And so in these kind of oscillation problems, you're going to see that you're going to see two things. You're going to see xsp, which is a particular solution, and then xtr, which is our transient solution. So the first thing we'll start with is finding, or I guess the first thing we'll do is a guess for xsp. We'll call it xspg. And so that'll be the right side. Oops. And like I said in the previous problem, whenever you see a sine or a cosine, your guess is always going to be a cosine, and then in this case 2t, because that's what it is here, in the non-homogeneous part, plus b sine 2t. And so now what you're going to do, now that you have your guess and there's no duplicates, now you're going to find x prime of sp, and you're going to find x double prime of sp. And then what we're going to do is we're basically just going to substitute all of that into this equation, and then we're going to use undetermined coefficients to solve for our a and b, and then we'll go from there. So what that looks like is like this. So we have xsp, I'll remove the guess part, and then we have xsp prime, which you just take the derivative. Remember, a and b are both constants, so you're going to get that plus 2b cosine 2t, then xsp double prime is negative 4a cosine of 2t minus 4b sine of 2t. And so now what we're going to do is we're going to take this and we're basically just going to substitute it into the left side there. And so what that's going to look like is a little bit long, so I'll scroll down a little bit like around there. So let's start with x double prime. So we have negative 4a. I'm literally just taking stuff from here and putting it here. And I'm substituting it into our equation. So I have negative 4a cosine of 2t minus 4b sine of 2t. And then let's see, now we have x prime, and it's multiplied by 2 in our equation. So we're going to say minus 4a sine of 2t plus 4b cosine of 2t. And now we have xsp again, and we're going to plug that into here and multiply by 5 because this. So we have plus 5a cosine 2t plus 5b cosine of 2t. And all of that is equal to cosine of 2t. Okay, so now we're going to start by gathering all of our, I guess you could call them like terms. So we have our cosine terms here, or I think I screwed something up here. Oh, this should be sine. Okay, so we're going to, there should be 3 cosine terms. There's 1, there's 2, there's 3. And we're going to gather the coefficients of those terms. So we have negative 4a, we have plus 4b, negative 4a plus 4b plus 5a. Negative 4a plus 5a is just a. So we're just going to have that. And then that equals 1. Why does it equal 1? Well, because since these are the cosine terms on the left side, we're just going to set all the coefficients of the cosine terms on the left side equal to the coefficients of the cosine terms on the right side. So we only have 1 cosine term here, and the coefficient is 1. So we're going to set a plus 4b equal to 1. And then now we're going to do the same exact thing with the sine terms. So we have here, we have negative 4b minus 4a plus 5b. Negative 4b plus 5b equal b. So we're basically just going to have b minus 4a equals, and since we don't have any sine terms on the right side here, it's going to equal 0. Oh, whoops. 0. And so we just solve this easy little system here. We get b equals 4a, and then we can substitute that into the top equation here, and we get 17a equals 1. Then we can find that a equals 1 over 17, b equals 4 over 17. And so now, do you guys remember when I found our XSP and we had a and b? So we're literally just going to plug in a and b back into our XSP, and I'm going to do that here. Our new XSP is now 1 over 17 cosine of 2t plus 4 over 17 sine of 2t. And from here we can find our c. So let's look back at our question. What now we have to do is write this into our form. Write our a cosine 2t plus b sine 2t into the form c cosine omega t minus alpha. So how do we do that? So how do we find c? Well, it's just a Pythagorean theorem. So we have square root of a squared plus b squared equals c squared, so root, and then we're going to do 1 squared over 17 squared plus 4 squared, which is 16 over 17 squared, and that just ends up being equal to root 17 over 17. So you can already take these answers out at least. And so now we found our c, and we also actually know our omega, and our omega is just the coefficient of the t inside of our cosine and our sine. So that's going to be 2, which doesn't eliminate anything else. So our omega is 2, so let me just write this somewhere. Our c is root 17 over 17. Our omega is 2. So now what do we have left? We have alpha left. So to find alpha, this is just going to require some memorization on your part, but you have to memorize this small piecewise function. So the formula for alpha depends on what the values of a and b are. So alpha is going to be tan inverse of a over b, b over a, if a is greater than 0 and b is greater than 0. So if both a and b are positive, then you use tan inverse of b minus a for alpha. For values of a, so when when A is negative, B doesn't matter in this case. When A is negative, you'll use pi plus tan inverse of B minus B over A. And then lastly, when A is positive but B is negatives, so when the signs are the opposite, then you're going to use 2 pi plus tan inverse over, or tan inverse of B over A. So in this case, our A is positive and our B is positive. So we're going to use the first scenario. So alpha equals tan inverse of, in this case, B over A would be 4 over 17 over 1 over 17, which is the same as tan inverse of 4. Oh, we don't have to simplify that. So we're basically done. Which answers does that leave us with? I think it's this one. And that is correct. Alright, so for number 3, we have a Mass-spring-dashpot system problem. So it says, consider a Mass-spring-dashpot system with a position function x of t satisfying, and it gives us an equation. And it says, recall that p equals c over 2m, omega naught squared equals k over m, and omega 1 squared equals omega naught squared minus p squared. Which of the following is the general solution to the equation above for the critically damped case c squared equals 4km? So these are our two important parts. One thing that I recommend you memorize specifically for like Mass-spring-dashpot system problems and like oscillation problems in general, or like mass spring problems in general, is this piecewise. So what you should always know is that c squared minus 4km, if that's ever positive, so think of this as when you're solving your characteristic equation with the quadratic formula, whatever's inside the square root is c squared minus 4km, pretty much. So if that's positive, then thinking about how your quadratic formula is going to break down after that, you're going to get distinct real roots. So your roots here are going to be distinct, and they're going to be real. And it's going to result in an overdamped system. This is kind of just something you should memorize, but if you think about it, it does make sense once you understand it. So c squared minus 4km, so whatever's inside that square root in the quadratic formula when you're solving the characteristic equation, if that ever equals 0, then if you just think about how the quadratic formula will break down if the square root itself, if that whole radical becomes 0, then what you're going to get is a repeated root, right? It's going to be real. It's going to be repeated and real. And that's going to result in a critically damped system. And lastly, if whatever's inside the square root is negative, right? If you have negatives inside a square root, you're going to get i's, so i's, imaginary i's somewhere, and you're going to get complex. Stuff. So if that's less than 0, what you're going to get is complex roots. You know, so your sine, cosine, solutions, all that. And what that's going to result in is an underdamped system. So if you understand this, relationship and how that works with the square root being inside the square root and the quadratic formula when you're solving the characteristic equation, then this question is really not that hard. You just have to understand this part, and you have to know what a repeated solution looks like. And in this case, it looks like this. It has e to the negative pt, p being the repeated real solution. And then you have c1 plus, and then times the quantity of c1 plus C2t. And the C2t is there because it's repeated. So we kind of already know that C is the answer, and it is. But I can also show you a way to solve this problem without having to memorize all of this. But I do still recommend understanding this relationship. Alright, so we're going to start with, like I said, the characteristic equation. So we have mr squared plus cr plus k equals 0. And from here, let's just plug it straight into the quadratic formula. So we have r equals, so we have negative b plus or minus square root of b squared, in this case it's c squared, funny enough, minus 4, ac is, a is m, c is k. We just make this km, and all over 2a, which is 2m. So hopefully this makes what I was saying earlier a little bit more less confusing. So we have c squared minus 4km here inside the square root, and we are given that c squared equals 4km. So essentially c squared minus 4km equals 0 if we just rearrange that, which turns this radical into a 0, right? If c squared equals 4km, so if all of this equals 0, then this whole thing turns into 0, and all you're left with is negative c over 2m. And if you look back here, where is it? Here, we're told that p equals c over 2m. So negative c over 2m would be negative p. So negative p is our repeated real root. So now if we build a general solution off of that, we can see that it's going to be c1 e to the negative pt plus c2 t. Remember, because we multiply it by t if it's repeated. So it's going to be like that. And you can easily see how this factors into this. I hope that answers this confusing question using two different methods. I really do recommend just understanding this relationship, the overdamped, critically damped, underdamped stuff, and how that relationship with what the general solution will look like in terms of distinct, real, repeated roots and complex roots. So for number 4, we have select the system of first-order differential equations that's equivalent to, and then it gives us this equation. These problems are a little weird at first, but they're actually not very difficult at all, and usually they're pretty quick. So what you're going to start with first is you're going to have x1, and you're just going to set that equal to x, and then you're going to have x2, and x2 is basically going to be the derivative of x1. So we can write it like that. And the derivative of x1, if x1 equals x, then the derivative of x1 is going to be x prime, right? So from here, we can take the derivatives of both x1 and x2. So we have x1 prime and x2 prime. And since x1 is x, since x1 is x, then x1 prime is going to be x prime. And since x2 is x1 prime, which is x prime, then x2 prime is going to be x double prime. So let me say that again. Since x2 is x prime, then x2 prime is going to be x double prime. And now we can use our given equation to find out exactly what x double prime even is. So we're just going to use basic algebra. We're going to subtract our 10x, or I guess add 10x, and subtract our 4x prime to the other side, and then we can divide by 2. So I'm basically using algebra to isolate x double prime from our given equation. And then we're just going to plug that back into here. So I have x1 prime. And since x1 prime is x prime, so x1 prime is x prime. But x prime we defined in the previous line as x2. So x1 prime is really just x2. And now we're going to find x2 prime. x2 prime is x prime, like we said here. And we found x double prime, or excuse me, did I say x2 prime is x double prime, and we found x double prime right over here. So we're pretty much just going to copy that into here. 10x minus 4 x prime over 2. And now we're on the finish line. So all we have to do now is we're going to substitute this x and this x prime for either x1 or x2. So x is x1 as we defined up here, right? So let me just so x is x1. And what's x prime over here? X prime can be written as x2, right? So, and all over 2. So this should be our answer. Let's see if it's anywhere in the... Oh, whoops, it's right there. It's just simplified, so e to the t over 2 is just 1/2 e to the t. 10x over 2 is just 5x. 10x1 over 2 is 5x1, and negative 4x2 over 2 is negative 2x2. So yeah, it's t. These types of problems are not too bad once you get a couple under your belt, but it's a little bit weird for sure. All right, so for number 5, it's we have a consider the system, and it gives us a system of DEs, and it says where alpha and beta are constants. For what values of alpha and beta is the origin a spiral sink? So remember, spiral sink is the key here. So if the origin is a spiral sink, then we know that our eigenvalues are going to have the form of negative p plus iq. And this is really just something you should memorize. So all spirals have the form p plus iq, and if it's a sink, the p will be negative. If it's a source, then the p will be positive. And if it's a center, there just won't be a p at all. So in this case, since it's a spiral sink, we'll have our eigenvalue as negative p plus iq. Another thing I'm going to do is I'm going to rewrite this into this form, just because I like it a little bit more. But yeah. Alright, so let's start this problem. So like I said, I'm going to rewrite this into a form that I like better, so I'm just going to take all the coefficients. We have alpha, sorry, I have terrible alphas. Cool. And then, yep, that's it. So now what we're going to do is we're going to find the eigenvalues of this system, of this matrix. So the way to do that is take the determinant. So we're going to do our alpha, other way around. Oops, I was doing it right earlier, my bad. So we're just going to do the minus lambda along the identity matrix, so the diagonal from left to right, from the left top to the top left to the bottom right. And then we're going to take the determinant of that. So what that gives us is, I'll write it like this so it's easier to understand. Since we're just multiplying this term times this term, and then we're going to minus this term times this term. So we're going to have alpha minus lambda quantity squared minus alpha times beta. So this is what that's going to look like. And we're going to set that determinant equal to 0. And from here, we're just going to solve for lambda, which is our eigenvalue. So we can pretty easily switch this. So alpha minus lambda squared is the same as lambda minus alpha squared. So and then I'm going to add alpha beta to the next other side. Take the square root of both sides, plus or minus. And then I'm going to add an alpha. So we finally have our eigenvalue. Our eigenvalue is alpha plus or minus root alpha beta. And so coming back up to here, we know our form should be negative p plus iq. And here our form is p, or sorry, this should have been plus or minus iq. So here we have alpha plus or minus root alpha beta. And so what that means is our alpha is going to be negative, since our form should be negative p, and our beta should be positive. And the reason for that is because we need complex roots, because it's a spiral, whatever's inside this square root needs to be negative, otherwise we won't get a complex root. And since alpha is already negative, beta can't be negative, because a negative times a negative would be a positive. And then if the square root was a positive, we would not get a complex root. So since beta is positive and alpha is negative, a negative times a positive is a negative, and a negative inside a square root gives us this negative p plus iq form. So alpha needs to be negative and beta needs to be positive. Okay, yeah. So I think the answer in this case is C. Alright, so for problem 6, we have consider the system, and it gives us a x prime equals ax type system. And it asks us, it gives us a defective eigenvalue of lambda equals 5, which means it's repeated. And it's asking us to find its general solution. So this problem is going to use this property. So we have a minus lambda I times v1 equals 0. So this is something you're probably familiar with. This is just how you find any eigenvector. And then the second one is what you do if you have a defective eigenvector or eigenvalue. So what this is you're basically, when you're setting up the solving for the second eigenvector, the generalized eigenvector, excuse me, for the defective eigenvalue, you're basically going to set, instead of setting it equal to 0, you're going to set it equal to v1, the first eigenvector. So if that doesn't make sense, it'll make sense in a second. So they tell us that our eigenvalue is lambda equals 5. And so what we can do is we can find the eigenvector. So to do that, we're just going to start by plugging it in. So we have 3 minus lambda, and then 7 minus lambda. And so we just plug in 5, since we already know the eigenvalue. We have plug in 5 for lambda. So 3 minus 5 is negative 2. 7 minus 5 is 2. And this is just basically putting into practice this property, this theorem. I don't know, I'm not a math major. That. And then we're going to set it equal to 0, a 0 vector. And so this is just a normal system. You can solve this by, we'll use the bottom part. So we have a plus 2b, essentially. A plus 2b equals 0. You can do the same thing by saying a equals negative 2b. And you can, to find the eigenvector, we can let a equal negative 2. We can let b, which means b will be 1. Which means we can write our v1 as, our first eigenvector as negative 2, 1. So that's pretty simple. It's something you're probably used to. That's just the normal process of finding an eigenvector. But the different part of this problem is the defective part. So now what we're going to do is we're going to find the, so for our defective eigenvalue, we're going to find our generalized eigenvector. So we're going to put into practice this second line, and so we are basically going to take exactly what we had before in terms of this part, and I don't know, we'll just call it a and b again. It's fine. And then instead of setting it equal to 0 like we did up here, the key part is we are going to set it equal to our v1. So instead of setting it equal to 0 up here, we're going to set it equal to our first eigenvector. And from here, you just kind of solve as usual. So we have a plus 2b equals 1 this time, which means that a equals 1 minus 2b. Now for the eigenvector, we can just let b equal 0, which means a would have to equal 1. And so we can have our generalized eigenvector, we can have our v2 just be 1, 0. Oh. There. And of course, if you use different values for the eigenvector, to me, it's okay. You'll be able to get the same answer at the end anyway, so it doesn't matter. This is just how I feel like the easiest way to do it is. So anyway, now we have our v1 and v2, and now we can calculate our general solution just based off of that. So this is what that's going to look like. We have x of t, and then we have, so this is what our, I guess, formula or our form is going to look like for repeated eigenvalues. So we're going to have e to the lambda t as normal, and then we're going to have c1 v1 plus c2, and it's going to be like this. This is somewhat different from when you don't have a system. This is kind of exclusive to systems of equations, but you'll see that in the next problem as well. So when you have a repeated eigenvalue, when you have defective eigenvalue, you're going to have your v1 for your second term as well. You're going to have your v1, but you're going to multiply it by t, and then you're going to add the generalized eigenvector in there. So this is what that looks like. So we have e, we have e to the, what's our lambda, 5t, then we're going to have c1, and our v1 is, what did we say it was, negative 2, 1, and our, and then we're going to have plus C2, and then we're going to have our V1 again, negative 2, 1. This time we're going to multiply by t, and then we're adding our V2, our generalized eigenvector, and that's it. And so from here, we can literally just, to put it in the form that the answers wanted in, we're just going to kind of combine it. So we have C1, and this is, I'm literally just expanding it. So we have that. So it's just, C1 times V1 times e to the 5t plus we have C2, and then this can be kind of made into one matrix, sort of. So we have negative 2t plus 1 and 1t plus 0, and so what that looks like in matrix is just the same, negative 2t plus 1. And then 1t plus 0 is just t, obviously. And then times e to the 5t. So I think that's what our answer looks like. Yeah. So number 7 says, it is known that the general solution of the system, and it gives us a system, and it gives us the general solution of that system. And it says, use a method of undetermined coefficients for systems to find the form of a particular solution. So it says, find the form of the particular solution to the non-homogeneous system, and it gives us the non-homogeneous system. So as you can see, the non-homogeneous part is this part. Because this is the same as that. So, which means that the general solution of this system is going to be this plus the particular solution of this. So we're trying to find the form of the particular solution, so just of this part. So the way we would start doing that is we have our guess. So we have, well, I guess the best thing to do to visualize this better is to split this off into two parts. So let's just make it 0 and 4e to the t plus 2t minus 1, 0. So this and this is equivalent. I'm just splitting it up because it'll be a little bit easier, I think, to represent the form. So, so thinking back to problem 1, kind of thinking the same way about forms and guesses, we're going to have our xp guess. And so let's take this into account. So our first guess, let's just do this one, 4e to the t. The guess for that would obviously be a, and I'm going to use the vector notation, a e to the t, because our leading term here, 4, has degree 0, so we're using our degree 0 polynomial in front. So a e to the t plus, and I'm going to use, for the next constant, I'm actually going to use c, not b, and you'll see why in a second. So for 2t minus 1, it's going to be ct plus d, obviously, because our polynomial is of degree 1, so we're going to match that. So we have ct plus d. And now we're going to check for duplications. So we're going to check for duplications with our general solution over here. So let's see ct plus d. Does ct plus d have any duplications in our general solution? No. Doesn't look like it. Let's see if a e to the t does. So here we have some constant and its eigenvector times e to the 3t, which is not a duplicate. But here we have c2 times our second eigenvector times e to the t, and which matches the form of this. So what we have here is a duplication. And the way we, I guess, unduplicate that is unique to systems. So if you remember in problem 1, we just multiplied it by t, or multiplied it by t squared, or depending on what the multiplicity was. In systems, which is unique to just systems, this procedure is a little bit different. You're basically gonna keep your a times e to the t, but you're gonna add a term, and you're gonna multiply that term by t, and so you have a e to the t plus bt e to the t plus c t plus d. So I hope that made sense. The duplication procedure was literally just adding a term and then multiplying that term by t. Whereas in a non-system, the duplication procedure would just be to multiply this by t, and then we wouldn't have this part. So if this wasn't a system, we would just have a t e to the t. But since it's a system, we have a e to the t plus bt e to the t. Hopefully that makes sense. I think that is the answer right over here. Yeah, it's right here. They have their coefficients a little bit different than me, but, you know, it's the same thing.